Hello and welcome to the first tutorial for ECO375. Today we are going to derive together the Ordinary Least Square Estimator. So first we'll start with a review of the linear regression model. Then we'll define the OLS Minimization Problem. To solve this problem we'll need to define the first order conditions, which have very important implications. And finally, number 4, we'll derive the OLS estimators, beta 0 and beta 1 hat. So let's start with the review. In the simple linear model, we have yi, which is a dependent variable, and xi, which is the explanatory variable that we can observe. And they are related to each other through beta 0 and beta 1, which we don't know. And there is some error term which we don't observe, ui. And because we don't observe ui, we can't directly get beta 0 and beta 1, so we'll have to guess them. So we'll end up with beta 0 hat, or best guess of beta 0, beta 1 hat, the best guess of beta 1, and ui. So graphically, we can see that we have a bunch of points which represent the data, and we want to find the line that fits the best through the points. So the equation of the line that we'll call y hat is beta 0 hat plus beta 1 hat xi plus this is a line, so there is no error term. So this, because there is no error term, it's called the fitted values. And if we take the difference between the fitted value, for instance here, and the points that we really have, this is the error term, ui hat. So our goal here will be to minimize the sum of the squares of the error term. And this is where the name of the method comes from, Ordinary Least Square, is because we want to minimize these squares. There are other methods where we will minimize the absolute value of the sum of the ui, or the sum of the absolute values, or you could take to the power of 4, but the most commonly used method is with a square. So as I said before, ui hat is basically the difference between the real y and the fitted value, yi hat. I can rewrite this as the sum of the yi's minus, and we know that yi hat is beta 0 hat minus beta 1 hat xi. Everything is squared, and this is what we want to minimize. So let's call this sum square residual, SSR. So we want to minimize this, the sum of square residuals over beta 0 hat and beta 1 hat. So sum of yi minus beta 0 hat minus beta 1 hat xi, and all of this squared. So this is the minimization problem. This is very important. And to find the solution, we'll basically need these first order conditions, which is to set the derivatives relative to beta 0 hat and beta 1 hat to 0. So graphically, we basically have a function that's always positive like this because it's a sum of squares, and the minimum is when the derivative is 0. So here we have two derivatives to take, one for beta 0 hat and one for beta 1 hat. So d SSR over d beta 0 hat is equal to, so the derivative of a sum is the sum of the derivatives. So we have the sum here. And then we have something squared, so the 2 comes in front. And then we have the same thing, yi is beta 0 hat minus beta 1 hat xi. And then we have to multiply by the derivative of minus beta 0 hat, which is just times minus 1. And we have to set this equal to 0. As we can see, we can simplify this because we can divide on each side by 2 and by minus 1. And now the first order condition becomes sum of yi minus beta 0 hat minus beta 1 hat xi equals 0. So this is equivalent. What is interesting here is to see that this is basically yi minus y hat, which is equal to ui hat by definition. This implies that the sum of the ui hat equal 0. And this is one of the important results. The sum of the error term is basically 0. Now we have the second first order condition, d SSR over d beta 1 hat which is equal to, let me rewrite the minimization problem. yi minus beta 0 hat minus beta 1 hat xi square. So if we differentiate this with respect to beta 1 hat, we get the sum. The 2 comes in the front, and then we keep the parentheses. yi minus beta 0 hat minus beta 1 hat xi. And then we have to multiply by the derivative of beta minus beta 1 xi, which is basically minus xi, and set this equal to 0. Again, we can simplify this by dividing by 2 on both sides and by removing the minus by dividing by minus 1 on each side. So this becomes sum of yi minus beta 0 hat minus beta 1 hat xi times xi equals 0. Again, this is equal to ui hat, the error term. So this implies that the sum of ui hat times xi equals 0. And we'll see later that this is basically this equal to, or this implies that the sample covariance between ui hat and xi is 0. So before I solve everything here, I need to go through a few results that will be very useful. And this concerns the sum of the product of two variables where we remove the mean. So sum of yi minus y bar times xi minus x bar. And this is equal to, I'm going to basically expand everything. So I take yi and I multiply by both elements in the other parenthesis. So sum of yi times xi. Then minus yi times x bar. And then I take the second one, x bar, and I distribute it on the other parenthesis elements. So minus y bar times xi and plus x bar y bar. Now we have a sum of sum and subtractions, so I can basically distribute the sum sign. We have sum of yi xi, then we have minus the sum of yi x bar minus the sum of xi y bar and plus the sum of x bar y bar. Because the x bar here, the y bar here, and the x bar y bar here are constants, we can get them out of the sum. They don't change with each term of the sum. So we can rewrite that as sum of yi xi minus x bar sum of yi minus y bar sum of xi, and plus, here we have basically plus n times x bar y bar that we sum together, so x bar y bar, like this. Now an important result that I'm going to use here, we know that x bar, the mean, is equal to 1 over n sum of xi. This is a definition of x bar. So this basically implies that n times x bar is equal to the sum of the xi. So if we look back here, we have n times the sum of y bars, and here we have n times the sum, sorry, n times x bar, n times y bar here, and n times x bar here. So if I rewrite that, we basically have sum of yi xi minus n times x bar y bar minus again n times x bar y bar plus n times x bar y bar. So we're going to simplify here, and we see that we have a much more simple result, which is sum of yi xi minus n x bar y bar. Now something here that we should note quickly is that if I take yi minus y bar and I just take xi, I don't take xi minus x bar. Let me distribute again here the x. So we have sum of yi xi minus y bar xi, which is equal to sum of yi xi minus y bar the sum of xi, which is equal to sum of yi xi minus n time x bar y bar. So we see that the first result we have here and the second result we have here are equal. So it means that whenever I have the sum of a variable minus the mean times another variable minus the means, I can remove one of the mean. It doesn't matter. So result, sum of yi minus y bar, xi minus x bar equals sum of yi minus y bar xi, which is equal to the sum of yi xi minus x bar. So I can choose to remove the mean from one variable or the other. It doesn't matter. And in the end, it's just equal to the sum of yi xi minus n time the means, the product of the means, x bar, y bar. Another interesting thing is that, note, the sum of x minus x bar square, so we use this for the variance, it's basically the sum of xi minus x bar times xi minus x bar. So it's the definition of the square. So we can use the same result here. It's the sum of xi minus x bar times xi, or the sum of xi times xi, so it's xi square, minus n time x bar times x bar, so it's x bar square. So important results here that we are going to use. If I come back a little bit, remember that we had the sum of ui hat times xi equals 0. So let me note that again. We had sum of ui hat xi equals 0. And we also have sum of ui hat equals 0. These are the two results we got from the first order conditions. The second result here, it just means that 1 over n sum of ui hat equals 0. So ui hat bar equals 0. So if we come back to the first equation here, we can basically rewrite this as sum of ui hat minus ui hat bar, because this is equal to 0, times xi. And if we come back to the result we have, it's basically the sum of a variable minus the mean times another variable. So we can write the long form here. So this equals 0, which means that sum of ui minus ui bar times xi minus x bar equals 0. I can take 1 over n here, and this is the sample covariance. So I put a hat on the covariance to indicate that it's for the sample. It's not the population covariance, which we don't know. But we can prove it to be 0, basically. So covariance, or we can show that it converge. So let me show you this. The population covariance here between the ui hat and xi will be 0 by the law of large number, but you'll see that later. So right now focus on the fact that the sample covariance between the ui hat and the xi is 0. Let me go back to our first order condition, and I'm going to derive the OLS estimator. So the first FOC we had, FOC 1, was that sum of yi minus beta 0 hat minus beta 1 hat xi, this must be 0. So I'm going to distribute the sum. So sum of yi minus sum of beta 0 hat minus sum of beta 1 hat xi, this should be 0. Again, beta 0 hat is constant, so we can get it out of the sum, and beta 1 too. So this becomes sum of yi's minus n time beta 0 hat minus beta 1 hat sum of xi. You remember that the sum of a variable, for instance sum of xi, is n time x bar. So we can rewrite this as n time y bar minus n time beta 0 hat minus beta 1 hat n time x bar equals 0. We are going to simplify here by n, and we have this wonderful result that says y bar minus beta 0 hat minus beta 1 hat x bar equals 0. I can rewrite this as beta 0 hat equals y bar minus beta 1 hat x bar. I note that I can also rewrite this y bar equals beta 0 hat plus beta 1 hat x bar. What does this mean? It means that when we have our data like this and our line, the OLS line goes through the point x bar and y bar. So if we take the average y and the average x, or lines that minimize the least square, will go through the mean. Let me put some red around that result because it's very important. And now we are going to go through the second result with the second first order condition, which was sum of yi's minus beta 0 hat minus beta 1 hat xi times xi equals 0. So I'm going to distribute the xi that's outside of the parentheses here. So this becomes sum of yi xi minus beta 0 hat sum of xi, sorry, minus beta 1 hat xi square equals 0. Going to break the sum. So we have sum of yi xi minus beta 0 hat sum of xi and minus beta 1 hat sum of xi square equals 0. And now I'm going to take the beta 0 that's here and plug it here. So we're going to substitute the beta 0 hat should I do it on the previous page? Yes, we have some room. So it becomes sum of yi xi, and then let me go back up so that you can see it, minus y bar minus beta 1 hat x bar times sum of xi minus beta 1 hat sum of xi square equals 0. We know that this is n times x bar, so let's put it inside the parentheses. So this is equivalent to, let me go a bit further. Sum of yi xi minus n times y bar x bar plus beta 1 hat x bar square n times again minus beta 1 hat, sorry, this should be a plus in the middle, so minus beta 1 hat and sum of xi square equals 0. Now this part here should look familiar. Sum of yi xi minus n times y bar x bar. It's one of the important results. That's here. Sum of yi xi minus n times x bar y bar. And we know that this is equal to basically n times the sample covariance between y and x. So this is equal to sum of yi minus y bar xi minus x bar. And I'm going to take the part with the beta ones and put it on the other side of the equal sign. So this is going to move to the other side. And we are going to have n times beta 1 hat x bar square minus beta 1 hat sum of xi square, and I can factorize by beta 1. So beta 1 hat times, I'm going to write the sum of xi square first, sum of xi square, and then here we have n times, when I switch it to the other side I forgot to change the sign, so this should be a plus and this should be a minus. N times x bar square. And this here should although look familiar because this is the second results we have here. Sum of xi square minus n times x bar square. So this is equal to beta 1 hat times the sum of xi minus x bar, the whole thing squared. So if we reorganize this a bit, we have beta 1 hat equals to sum of yi minus y bar xi minus x bar over the sum of xi minus x bar square. I can multiply in the top part by 1 over n and in the bottom part by 1 over n. So it's equal to this is the formula of the sample covariance, cov yi xi, and at the bottom is formula of the sample variance, var hat x. And these are two important results. Let me write a summary. Of what we did today. So we've seen that sum of ui's is 0 and sum of ui's hat xi equals 0. This implies that the sample covariance between u hat and x is 0. So that the first result, second result, beta 0 hat, it's equal to y bar minus beta 1 hat x bar. And last result, beta 1 hat is equal to sum of yi minus y bar xi minus x bar over the sum of xi minus x bar squared, and this is basically sample covariance between y and x. And over the sample variance of x. Oops, a bit too much. I hope I didn't go too fast and I didn't make too many mistakes, and I'll see you for next tutorial.